Hello everyone, welcome to your week 6 video lecture. This is the only video lecture of this week, although it's going to have a lot of important information we will utilize the rest of this unit. And remember, we did have an introduction synchronous lecture comparing ionic and covalent bonds. We're going to move on from that with this. And you got yourself a pretty good chemistry cat joke right there. But we're going to start to kind of look at the basics of bonding here. So focus on what's in red. And again, I highly suggest writing this down so you can go back and quiz yourself and study for the next unit test. And so let's go back to Unit 1 in configuration. And if we were to look at the configuration for sulfur, 16 is the atomic number, which means for a neutral atom, we'll also have 16 electrons. We'll fill into 1s2, 2s2, 2p6, 3s2, and then end at 3p4. And that should make sense if you look at your 3p on your periodic table. Sulfur is the fourth element over. But I wanted to focus on the green electrons, and these are called valence electrons, which we will define on the next slide, but they're in the highest energy level. And so notice the first energy level is represented, the second is, but the outermost highest energy level represented is the third energy level. And what we'll realize too is by totaling up 2 plus 4, we'll realize that sulfur has 6 valence electrons in the highest energy level. Now these electrons are called core electrons. Not that they're not important, but they don't participate in bonding, which is what we'll learn on the next slide. That's why we focus a lot of our attention on valence electrons. We can predict a lot of things about an atom based on how many valence electrons it has. And shorthand configuration will match. So again, we're going to start with neon as a noble gas. You'll notice you have 3s2 and 3p4 again. And I'm sorry, that's getting cut off a little bit, but you get the idea. It's the same thing we're seeing here. It still has 6 valence electrons. And again, those are the outermost electrons observed. And this is why we use the noble gas as a starting point, because then we'll always get our highest energy level to show us the valence electrons. So let's define both of these terms. The core electrons are those inner energy level electrons that are closest to the nucleus. And the outer energy level then are those the valence electrons. And those core electrons are kind of boring. They don't really participate in bonding, and so they're there, but they're not the ones that are involved in chemical bonding. So again, that annoying animation there is to really have you focus on the idea that it's the valence electrons that participate in chemical bonding. So if we were to look at some examples here real quick, helium. So remember, helium only has 2 electrons to fill in, so it's 1s2. So the outermost energy level for helium is the first energy level, and you've only got 2 valence electrons. Now, as you recall, as we talked about noble gases a little bit ahead of time, or for the last unit, and all of these are noble gases, remember that helium is an exception with 2 valence electrons. If you look at neon, we'll start at helium this time, and we'll have a 2s2, 2p6. Outermost energy level is the second energy level, 2 plus 6. We have 8 valence electrons. Argon is going to be similar, except we've moved to a higher energy level. The highest energy level represented is the third. 2 plus 6, 8 valence electrons. And then finally, krypton. And this is a good example because notice that we have 3D, but the outermost energy level represented is the fourth energy level. And there's an S2 and a P6 there. You get a total of 8. 8 valence electrons is the most valence electrons you will have. 8 is the maximum. And that'll make sense when I show you how this applies to the periodic table. So just take a peek here. Notice that you have a full S and a full P. And we had talked about before that noble gases are stable and unreactive and low energy. But now you realize it's because they have a full S and a full P. So notice that each of these, again, helium being the exception, but each of these has a full S and P. D's do not contribute, at least in the way we are talking about this, to the valence electron count. So let's talk about an important rule that's going to guide us through this entire unit. It's called the Octet rule. I'd mentioned before to some classes that really when atoms are bonding, whether it's covalently or ionically, it's that they're jealous of the noble gases. And we don't want to personify atoms too much, but they want that stable, low energy configuration. So they'll lose, gain, or share electrons to do it. And that leads us to the Octet rule. Atoms want to fill their valence orbitals, the S and P, with 8 electrons. So if you have a full S and a P, that's 8. And that makes, again, makes that configuration like a noble gas, where it's stable and low energy. Remember, helium's an exception. So if you look at something like lithium, which is going to be the element after helium, lithium's going to want to be like helium in terms of its configuration to be like a noble gas. So just realize that the elements, are helium included, the elements around helium are going to be exceptions to the octet rule, but all of the other elements and those atoms that represent those elements want octet. So now it might start to make sense why we had you work with the periodic table groups as we did. You skipped the transition metals, so we didn't have you number those for your groups. You have S1 and S2 here. And then as you move across, this would be P1. But remember, you're coming from an S2. So here, if you think about it, this group 1 all have 1 valence electron because they're all S1. That's it. Group 2 here all have 2 valence electrons, S2. This group all have 3 because they're going to be S2 and then P1. So total of 3 valence electrons, and it goes all the way over here to 8, right? So octet. Remember, helium is an exception there, but neon and down all have 8 valence electrons because they have S2 and P6. So now hopefully it makes sense a little bit of what we were doing and trying to get you to skip these transition metals when you made your periodic table. So to quickly define a chemical bond is the electrical attraction between the nuclei and the valence electron of different atoms. So notice down here we have sharing of electrons. So if you think back to the synchronous lesson, this is a covalent bond. This nucleus here, this is going to be hydrogen because I see 1 proton and 1 proton, and so atomic number is 1 is hydrogen. But this nucleus here, this proton, is attracted to the electron of the other atom. Now the way this is being shown, we don't really know which electron was which, but the idea is because they're attracted, they're going to start to overlap, and that overlap allows them to share those 2 electrons. So remember that helium is an exception. Hydrogen only actually wants access to 2 electrons to be like the noble gas helium. Now, why do any of this, right? Why form chemical bonds in the first place? Why try so hard to look like a noble gas? It's about energy. So energy is given off when bonds are formed. And this is one of the biggest misconceptions of chemistry students. So energy is released, it's given off when a chemical bond forms. And again, we just said that forming bonds, whether it's transferring or sharing of electrons, is going to get noble gas configuration. And that is going to allow for the release of any extra energy as we get a low energy, stable configuration. So ultimately, atoms bond together to have a lower energy, thus greater stability. So again, all of these chemical bonds and all of this work to look like the noble gases in their electron configurations is to have a lower energy. And again, because the noble gases already have that perfect full octet or duet for helium, they don't react. So then what would this octet idea look for ionic bond and compound? So if we look at chlorine, 17 protons, 17 electrons for a neutral chlorine. And chlorine's wondering, well, how can I be like a noble gas? Because I'm not right now. If you think about its configuration, notice the outermost energy level is 3. 2 plus 5, this has 7 valence electrons. It wants 8. It is 1 away. A number of you talked about halogens, because if you notice chlorine's position, it is in the halogen group. They will all have 7 valence electrons, which means they're all highly reactive. And this is why they're highly reactive. They are going to work really hard to try to look like a noble gas since they're so close on the periodic table. So what does that actually look like? Well, it either gain 1 electron, and think about it, if it gains 1 electron, it has 18, and it would look like argon. Or it could lose 7 electrons. If you subtract 7 electrons from the 17 it has, it's going to have 10 electrons in its configuration, and that looks like neon. So which is it going to do? It's going to do the easier one. It's going to gain 1 electron. Because when it gains that 1 electron, again, notice it's still chlorine, protons don't change, but you've got the 18 electrons now. Well, again, take a peek at the periodic table. Argon has 18 electrons naturally in its configuration. By chlorine gaining 1 more electron, it now has octet. Instead of just having 5 in the P, it now has 6. 2 plus 6, you get the octet, and it's now going to be very energetically stable. Now remember, it gained an electron, so it does form an ion now, thus ionic compounds and ionic bonds. So the take-home point here is that chlorine is going to be more stable energetically if it gains 1 electron and forms an ion. And then finally, what would this look like for covalent bonding? So let's take fluorine, which again, if you look at the periodic table, is a halogen. So if you think about its configuration, and this is just, it's called an orbital notation. You don't need to know this. It's just a visual way of looking at a configuration. Notice we're looking at the outermost valence electrons. I've got 2 here, and then I've got 5 here. So there's those 7 valence electrons again. And that makes fluorine really want 1 more. However, let's say that there isn't an electron available to gain. But let's say this fluorine has a friend. I really got to stop personifying atoms here. But let's say there's another fluorine around. Notice it also has its 7 valence electrons. And again, there's no electrons around to gain. But if we have a covalent bond, and this is a little bit hard to animate, but the idea is if those fluorine atoms overlap their p, notice what happens. They can share those 2 electrons. I know this is a little bit odd, but I've got 1, 2, 3, 4, 5, 6, 7, 8 electrons available to this fluorine in the outermost energy level. And I've got 1, 2, 3, 4, 5, 6, 7, 8 for this fluorine. Now, do those 8 belong exclusively to each of those individual fluorines? They don't. But by overlapping and having that attraction, and again, you got to picture the weird those 3D petal shapes for these orbitals. But by overlapping, they can share electrons and they feel like they have an octet, even though they don't have their own individual octet. So this would be how a covalent bond is able to achieve octet. So there's some important stuff here in terms of octet. We're going to continue to refer to that. But what the next set brief notes will be is how do we show these valence electrons. Okay, so let's move on to something called electron dot notation. It's really not too bad. We'll get through it pretty quick here. But since electron dot notation is so fun, I feel like that calls for another Chemistry Cat joke. Moving on. So this is in red, and you're not going to be asked to define electron dot diagrams on a test. I mean, you're going to need to recognize them or make them. So it's in red, and if you want to write it down, it doesn't hurt. I think just you'll get used to doing them, and you don't necessarily need to follow the instructions I'm about to show you. But the reason we cover this is electron dot diagrams allow us to show valence electrons, and we just talked about how important valence electrons are. So here are the directions, and like I said, you can pause and write those down if you want. Otherwise, if you've watched me do a couple of them, I don't think it's going to be too much effort for you. First thing you're going to do is write the symbol. And I'm going to make up a symbol here, X, not on the periodic table, we're just making this one up. And then what we want to do is put a dot, thus the dot diagram, but a dot for each valence electron. And you don't want to pair up until they have to. That's it. Those are the 3 rules. Let's say that this X element has 8 valence electrons. So this is how we would organize them. And I think if you're following along, you'll notice a connection. Remember that the max amount of valence electrons you'll ever have is 8. And remember, they're coming from an S, which only has 1 orbital. And they're coming from P, which has 3 orbitals. So remember that each of these can hold 2 electrons. And just notice how you've got 4 positions, each of these representing an orbital, to allow those 2 electrons. So you have a total of 8 maximum. And again, these kind of correspond to the 4 orbitals coming from the S and P together. So that's the connection there. And like I said, I know this is going to be a noble gas because I count up 1, 2, 3, 4, 5, 6, 7, 8 electrons, valence electrons. So I know that's a noble gas. So that's kind of how you use these. So let's do one together really quick for nitrogen. As you look at your periodic table, you'll realize that nitrogen has 5 valence electrons. 2 ways to do that. You can just look at nitrogen's position, look above it. You should have written a big number 5. That's the number of valence electrons. Or you can look at nitrogen and realize, well, it's going to be an S2, specifically 2S2, 2P3. So the outermost energy level is 2, and 2 plus 3 is 5. So either way you look at it, that's going to be the number of valence electrons we are filling in. So you find that symbol, it's N. Great. Write it down. Next, we want to add electrons, but we do it one at a time. It doesn't matter where you start. So I usually start on top. And I should mention, there is a specific way you are supposed to fill in for dot notation. We are not worried about that this year. If you're really interested in the proper way, I can teach you sometime. But it's really kind of beyond the scope of this class. So I usually start at the top. So I'm going to put 1 electron. I've got 4 more to go because I have 5 valence total. and then I'm going to move to an empty, and then move to an empty, and then move to an empty. And again, this kind of is following Hund's rule, and that's where the disconnect is, like we're not quite doing this correct. But fill empties first. We've got one more valence to go. Now we've got to pair it up. And I don't really care where you pair it up. If you're like, you know what, I'm going to pair it right here instead, fine, and then don't put it there. So it really doesn't matter, but you would need to have, when I look at your nitrogen configuration and your notation, I would need to see one that's paired up and the other ones are single for a total of 5. So that's it. I'm not even going to really work you too much through this practice. If you look at sodium's configuration, it's going to end in an S1. So the outermost energy level is the third, which means 1 valence electron, or just look at sodium. And right above that group, you should have a big number 1. So there's your 1 valence electron. We're going to move over to magnesium. Ends in S2, 2 valence electrons. There you go. I mean, honestly, I think you get the idea. Carbon, again, look at its position, should be a big number 4 above it, or realize it's S2, P2 for a total of 4 valence electrons. Put 4 around it. Notice we haven't paired them up. You got to fill the empties first. I think you get the idea. You can slow things down and think through this and treat this as practice. The oxygen has 6. Fluorine we've talked about. We know with the halogen it's 1 away. So 2 plus 5, it has 7. There's the 7. Notice there's only 1 that is unpaired for that electron there. Beyond the noble gas, we've talked about those, all 8. So there's that full S&P represented as a dot diagram. Helium is the exception. And technically helium, you should pair it up. I'm not going to ever bust you on that. So it's fine. However you want to show helium is fine, but it only has 2. So here you go. We've talked about this a bunch. Any trends? Well, I've told you a bunch. I know this is in red, but just realize the group number. Again, we had you go 1 through 8 only. Skip the transition metals. Group number corresponds to valence electrons. So if you know that, it's going to make your life much easier. You can just look at position on the periodic table, and you'll know that sulfur has 6, or chlorine has 7, or silicon has 4. All right, finally then, what we're going to realize is when we do these dot diagrams, we can kind of incorporate the idea of cations and anions here. So I want to just point out, I'd mentioned this already for ionic bonds, but metals, remember ionic bonds are going to be a metal and a non-metal. The metals are going to always lose electrons. And if you look at their positions on the periodic table, they always have 1, 2, or 3 in our world of first year chemistry, 1, 2, or 3 valence electrons. So they're going to lose 1, 2, or 3. Right? If you have 2 valence electrons, it's much harder to gain 6 electrons to get 8. You lose the 2. So then what does that look like? So let's look at sodium as an example. And this is going to be a little bit confusing. And so I think it's important if you need to rewind and go back through this, it's not a bad idea. So notice the configuration in the outermost energy level for sodium is 3s, and there's only 1 electron in it. And so it has 1 valence electron. Position on the periodic table should make sense with that. Now, again, it could lose 1 electron, or could try to gain 7 to get octet. And what you will find is it's going to lose. Metals will always lose electrons. And so it's going to lose 1 electron. And that means if it loses an electron, it's going to be a cation. So now it has 1 more proton than it does electron. Notice that when we lose an electron from this outermost energy level, it's no longer occupied. We don't count it as the outermost energy level anymore because there's no electrons there. So now what's the outermost energy level? The second. And notice 2 plus 6, there's your octet. So by losing the 1 electron out of its outermost energy level, we no longer worry about 3 being the outer energy level. It's now 2, and that 2 is full. It's a noble gas configuration. It does have a positive 1 charge, but it has gained noble gas configuration by losing an electron. So what does that look like in the diagram? And again, just metals will have fewer valence electrons, 1, 2, or 3 for our purposes. It's not quite the truth, but let's look at calcium. So calcium is alkaline earth metal. So the outermost energy level represented is 3s with 2 of them. So it's going to have 2 valence electrons. And we would show our configuration like that. But remember, metals are going to lose electrons. And think about it, if we lose 2 valence electrons, that third energy level is no longer occupied. S2P6 is now going to be the outermost energy level. 2 plus 6 is 8. And also, too, just look at the configuration for 2s2. 2p6, that's neon. And so by losing those 2 electrons, calcium can have the same configuration as neon. So how do we show that for a dot diagram? Well, we really don't. Remember, these 2, what were out in the 3s energy level, are going to go away. They're gone. So this energy level is no longer represented, and we form a 2+ charge. So I know we've been showing you and having you show charges. Well, this is kind of how that happens and why it happens. So we don't really do a dot diagram for a cation, but we do need to show the charge. So it'd be a calcium with a 2+ charge. And then finally, how about an anion? So nonmetals, and again, think about ionic compounds. We know the second element is going to be a nonmetal. Well, the nonmetals are going to gain electrons. If you think about it, and again, we're simplifying things, but generally, like the nitrogen group wants 3, the oxygen group wants 2 more to gain octet, the halogens, fluorine group down that way, wants 1 more, so they're going to be gaining electrons to get to the octet. They don't want to try to lose 7 electrons, that's too much work. And because they're gaining electrons, they're going to form negative anions. And again, if you kind of think about a configuration, it should make sense. So here's sulfur, outermost energy levels 3s, 2 + 4 gives me the 6 valence electrons. And again, it is too much work to get rid of 6 electrons, easier to gain 2. Now, if it gains 2 electrons, notice now the outermost energy level, which is still the third, 2 + 6, it's got 8. And in terms of noble gas configuration, it's going to look like argon. But it gained 2 electrons, so it has a -2 charge. And so again, visually, and I just had sulfur, and then I changed to phosphorus. I apologize. So phosphorus, when you count up its valence electrons, it's 5. So I have 1, 2, and then 3, 4, 5. Notice to get 8, it wants 1 here, 1 here, and 1 here. So it's going to gain 3 electrons. Remember, that's gaining a negative charge with each of those electrons. And so ultimately, phosphorus would have a 3- charge. So we're not going to ask you to show dot diagrams, but we wanted you to understand the dot diagram connection to both a cation and an anion. All right, there's one more thing to talk about in this set of notes. And again, this is going to be very, very important moving forward as we get into naming. I want you to take a look here. I've got ions. These are all metals right here. So notice each of these has a +1 charge, and so it lost 1 electron. Here's group 2, and so they have a +2. They lost 2. Metals will always lose. Aluminum's a good example of a metal that would lose 3 electrons to form a positive charge. And look at how we name them. Now come over here. These are the nonmetals. Notice something like nitrogen has 5 valence electrons, but if it gains 3, it gets octet, but it's going to gain a 3- charge. So we have phosphorus, we have oxygen, right? Oxygen is going to gain 2 electrons. Here's halogens. They're going to gain 1. Notice what happens to their names. So metals, nonmetals. Notice that we're going to change the name as an ion. So if I just look at N, that's nitrogen. But if it's N3-, that's an ion, it's nitride. So then what's that all about? Here it is. Cations, just use the name. So cations are always going to be metals now we're learning because they lose electrons, leaving behind a positive charge. Anions, you need to chop the ending and put "-ide" to show that they are anions that have gained electrons to get octet. This may or may not make a whole lot of sense why we need to do this right now, but as we get into naming and ionic stuff in about a week, you'll start to see this pop up again. So for now, we want you to understand this, that as ions, we need to show that they're ions, specifically anions, and we do that by changing their endings. So nitride, phosphide, oxide. So if I tell you have oxide, you know you have oxygen with a -2 charge. If I tell you have oxygen, you have oxygen that's got it's 8 protons and 8 electrons, and it's neutral. Again, it's not energetically favorable as just a regular element, but oxygen means just regular element off the periodic table. Oxide means an atom of oxygen that has gained 2 electrons to form an anion. So that's it for this video lecture. And again, this is the only video lecture of this week, but there's a lot of important stuff in here. So please come back to this as we work through the week and let me know if you have any questions. Until next time.